these slides that we're going to be looking at are available in the online course materials. If you scroll down to the bottom, you'll see uh, first you'll see the school year support kickoff meeting. That was the previous meeting. So if you didn't get a chance to see that, you can open that video there and rewatch that. So we're going to take a look at the program timeline and constraints. So if you open this up, you'll see there is a PDF version of these slides right here. So anytime you want to come back and look at this, that's where it is. All right, so to start off, let's take a look at the timeline again. Um, so we started on October 2nd, and our first milestone was November 1st, which was to submit a 2 to 3 paragraph experimental proposal. Now, don't get worried if you haven't done this yet. We're going to be much more lenient than, say, one of the rocket companies that we normally would fly with would be. Um, the whole idea here is to give everybody kind of a taste of what the process looks like for launching an actual CubeSat into orbit. And so we wanted to give you the opportunity to kind of experience that by having to meet certain milestones and expectations. Like I said, we're going to be much more lenient with you. So don't worry if you haven't submitted it yet. Um, you're more than welcome to do that. Continuing on. Ideally, you would have it submitted by at least December 2nd at the latest, just because that's when the logical designs are due, the next milestone, and wouldn't really make sense to try to submit a logical design if you haven't already submitted your 2 to 3 paragraph experimental proposal. So you can take a look at the expectations. Now, the constraints are important. Ultimately, we can't be too flexible with these constraints because this is just the nature of building CubeSats. Like for one, if you do not build your CubeSat as a 10 centimeter cube, then it's technically not a CubeSat, at least not a 1U CubeSat, which is what we're looking for. The mass is important as well because we can only fit so many CubeSats on any single flight platform, and the mast is a big part of that, especially when it comes to high altitude balloons, which is what we are planning on flying all of your CubeSats on initially. So please keep within those guidelines. Um, like I said, the timing is flexible more so than it would be if you were, say, submitting your CubeSat to a flight provider like Blue Origin or Firefly Aerospace, or folks that we've flown CubeSats with in the past. Keep in mind that this particular CubeSat that you're building will go up to the edge of the atmosphere. So it has to be able to withstand very low temperatures, low pressures, and potentially high humidity. If it's flying up through clouds and whatnot, it might get some direct, condensation on it. Keep that in mind. And as far as power, it's going to have its own power source. So a lithium polymer battery would be ideal. And all of these sensors and batteries and such, I have a spreadsheet that includes where to find these so that if you're looking, you'll be able to find those with ease. And always, if you ever have a question in regards to sensors or batteries that you want to use, you could always just send me an email and I can give you some time to talk about that, and we can kind of brainstorm what would be best for your particular situation. Try to stay away from hazardous materials, nothing that will burn or explode. I know that LiPo batteries do have a tendency to do that if cut open, but ideally that's not going to happen on these flights. So no other explosive materials or anything like that. And ideally, too, you will want to vibration test your CubeSat before sending it in. And this can be as simple as just, holding it in your hand and shaking it around quite a bit, or having one of your students do that. Or we've had people tie a string around them and swing them around over their head. Or you can even come up with your own little vibration table. Um, you know, it could be some sort of vibrating device that is attached to a surface that would cause the CubeSat or whatever you put on there to vibrate around for an extended period of time. That is really the thing that would most likely um, cause your CubeSat to cease working. Um, just because it's easy for wires to come loose and whatnot. My recommendation is to use something like E6000 is a type of um, like hobby cement. It it's a really good one for this because when it solidifies, um, it turns into kind of like a rubbery plastic material, which is good because it can absorb vibrations, but also after you've put this all together, if you decide you want to modify or reuse parts from your CubeSat build, it's this particular type of um, is easy to take off. And again, that's E6000. All right, so when it comes to putting together your proposal, as you have seen in either the course or if you came to one of our in-person workshops, you'll see that I talked about NASA's BEST, or Beginning Engineering, Science and Technology Engineering Design Process. This is really a blueprint or a framework for coming up with testable questions. Um, it's not unlike the scientific method that you start by asking a question, then you start coming up, you brainstorm solutions or hypotheses, and then you have this kind of circular portion where you plan by getting together with your students and coming up with a design. Then you start working on building that design, then you have to test that design, and more likely than not you will realize that there are things about that design that can be improved, and so you'll go back through that whole process until you are satisfied with your design. And then once you've done that, you can start sharing the results, whether that be um, publishing the data itself, making graphs and charts, or by going to a conference and sharing at a conference, or just with your local school community. Ultimately, that's the goal here. The goal is to get you and your students contributing to the greater scientific community with your CubeSats. So choosing a testable question, see this image here. This is kind of what the process looks like. At first, it might be like really crazy and convoluted. You might have lots of different ideas from your students. And the goal is to kind of narrow it down. And towards the end of the process, it should be a pretty straightforward thing that you're working on. So, don't, again, don't feel, too worried if you don't have that testable question yet. That this is the hardest part, is like taking those first couple of steps. And I'm here to help you along the way. So please utilize me in any way that you can. If you want to schedule a time to talk in an online meeting format or on the phone, or if you want me to talk directly with your students, I'd be happy to do that. I can answer questions directly from them. So, I mean, think about with your students, what is something that they're interested in? What is something that is relevant to them? Depending on where you are in the country or the time of year, there might be certain things that are particularly relevant to students. I'm in northern New Jersey, and right now we are experiencing a lot of wildfires that are going on because of the severe drought. And so I know that students at my wife's high school are doing projects based on air quality that is affected by the smoke from the wildfires. Seems like wildfires are a more and more common thing in our lives. And, that might be something that is relevant to your students. Maybe you are in an area that has a higher than average ambient radiation levels, maybe radiation experiments or something that would be interesting to your students, especially for our New Mexico teachers. I know that there have been lots of things related to nuclear tests and whatnot in the state of New Mexico. Maybe that's something your students would be interested in finding out more about. Just as an example. Um, then, so once you have, you know, have some ideas for questions, you're going to want to narrow that down a bit. Um, ultimately, only so many sensors can fit inside of one of these 1U CubeSats, or due to the constraints, only so many questions can actually be, worked on in a single CubeSat. Also, it's important to make sure that there are actually sensors that are available to collect data on that question, um, and that they fit within the constraints. Like going back to the radiation sensors can tend to be a little bit more expensive than other sensors, where the average Arduino sensor is anywhere from like $5 to $25. Some of the cheapest radiation sensors are like $70, and the more expensive ones can be hundreds of dollars. So, it just might not fit within the budget of the project, or maybe they're just too big. Um, I know I'm thinking of one brand in particular where, actually, I have them right here. So these sensors right here, if you can see my little screen somewhere, if not, I'll show you later after I'm done sharing my screen. But these guys are actually pretty big. Was able to fit two of them into a 2U, but trying to fit even just one of these into a 1U is hard. It can be done, but there's not going to be very much room or weight left after you do that. So then once you've whittled it down to a specific question that you want to work on, then you're going to start thinking about your logical design. So the logical design is essentially telling us, what does your experiment seek to accomplish? So you have your testable question. You're going to start assigning roles and responsibilities to students. And bear in mind that just because you have a student in your class that is not interested in STEM doesn't mean that they can't be involved and even excel in this project. I'm sure that you have students that are very interested in social media, and social media can be a big part of this. Documenting the whole process, the designing, the building, the collecting of data, all of that can be shared on social media, and maybe you have one of your roles for a student be social media manager. um, Not everything in these CubeSats has to be strictly engineering based. You could potentially, add art into your CubeSat. We've had students from uh, around the country who have, integrated three-dimensional and two-dimensional art into their CubeSats, whether they were poems or paintings or sculptures. All of those things can go into these as well. So really try to think about how to get every single one of your students involved, even if it doesn't seem like this is something that's really up their alley. You'd be surprised what you'll, find for students to do. And then, probably the most important aspect of the logical design is a written step-by-step description of, how the experiment is going to work. So, the experiment is, turned on, whether that's with a switch or connecting a power source. Then after, various sensors boot up, they will start collecting data. What is that data? What kind of data is it going to be? Is it going to be in the form of numbers, or will it be charted in some way? So we're just trying to get a general sense of, what is the process of this CubeSat collecting data from the moment it receives power to the moment power is disconnected from it. And that can be like a page, maybe two. The physical design is going to be a little bit more in depth. It's going to be similar to the logical design in that it'll show, how the experiment actually works and how the CubeSat works. But we want to know specifics now, like exactly which sensors you're going to be using or other equipment. We want to see a wiring diagram, whether you use a computer-based program to make that, or you use Paint, or you use just pencil and paper and draw it out. That's perfectly fine. Doesn't have to be anything in particular. It just needs to show us the sensors themselves and how they're going to be connected to your Arduino. Then we'll also want to see the Arduino code or sketches that you've come up with to run all of your various sensors just to validate that it's all going to work. And then we'll want to know, exactly what data is being collected, how it's being collected, how often it's being collected, and that will, encompass the physical design. Essentially, that is the last step before actually putting this all together. You've now determined, what the equipment is going to be, how it's going to be connected, and essentially it would be almost like a set of instructions for putting your experiment together. And then the engineering model, it's more this in this particular instance, this is going to be more than an engineering model. This is going to be your actual CubeSat. Um, if you were building a CubeSat to go into space, you would build two of them. You would have your engineering model that you would keep on your test bench that would be used to, you know, validate that the experiment is going to work. But then if you were to say have something happen after launch and your satellite is in orbit, you may need to figure out why the satellite is behaving in a certain way. You can do that with your engineering model and potentially fix any issues that are going on in your actual flight model that's up in orbit. In our case, for this program, our engineering model is also going to be our flight model. Um, you're more than welcome to build multiple CubeSats. Um, it might even be something that you should do so that your students can then compare and contrast how the flight model worked versus how this engineering model worked, but it's not required. So you're going to utilize your logical design to build that initial model, and then you'll use that to troubleshoot, program, you know, anything that takes place during the build, and you'll be able to collect some initial test data from the sensors so that you can confirm that it actually all works. Before you send anything to us, we want to validate that the CubeSat actually works, because it would be terrible if you shipped it all the way across the country and it showed up not working. I will be testing all of the CubeSats once I receive them. And, as long as it's nothing major that's wrong, um, I should be able to work with you to get it working. If it shows up and it's just a box full of parts, I'm not really going to be able to help you out there. But if something happened during shipment, which does happen. I mean, even we have to ship our CubeSats to flight providers, and things can happen en route. So, it's understandable, and we will work to make sure that your CubeSat is ready to go before we fly it. So in these slides, this right here is a link. This might be a good thing to take a look at. This is just a update from earlier this year that goes through some of the previous workshops that we've done, as well as some of the payloads that we've flown. So I was just showing this right here, BO2U2. This was one of the two CubeSats that we flew with Blue Origin last year. You can see those big radiation sensors there. Then we also flew in 2023 CubeSats from various classrooms from around the country on the Perlin Stratospheric Glider down in Argentina, as well as on the egret tow plane, which that's what you see here in this picture. This is what tows Perlin up into the air before releasing it and letting it fly on its own. So here are just those CubeSats being loaded into Perlin right here. And this is them getting ready to fly Perlin. They're aiming to break the world record for a piloted aircraft without engines. They're trying to reach 90,000 feet, which would, I do believe it would break the record for altitude for all aircraft besides rocket planes like the X-15. So really, the reason I wanted you to look at this is not necessarily for that stuff, but down here towards the bottom, you'll be able to look at some of the CubeSats that were previously flown on Perlin, as well as on high altitude balloons. And this could give you a little bit of inspiration, perhaps, or guidance onto what types of sensors have been flown before. Now, it would be absolutely awesome if you came up with a completely unique CubeSat build. But that's not absolutely required. So gain some insight from these if you want to mimic some of these and compare your data to previous CubeSat flights. That's fine too. Maybe mix and match. Take a little bit from one of these and maybe a little bit from another. So here's one of those examples of CubeSats that had art on board. They had a poem as well as a couple of paintings here. This one right here, actually, these are 3D printed, uh, like rocket, planet, and some stars on there. So not just 2D, but also 3D art. So yeah, take a look at this. Maybe use it as inspiration, show it to your students just to get an idea of what is possible. All right. So then, oh, also I've been emailing these out pretty regularly. You've been getting these in your email from me maybe every other week or so, sometimes even more often than that. These are the standards alignments that I put together. So I went through the next generation science standards, and I know not every state uses the next generation science standards, but based on what I've seen, even if your state doesn't use those, your standards are probably pretty similar. I know that some states that don't use next generation science standards do, however, use them as the basis for their own standards. So feel free to look through here because what I did was I took the standard and the clarification statement that goes with it, and I wrote down how I see the alignment between the standard and using CubeSats in the classroom. I've since updated all of them with sample questions as well and links to resources that apply to that particular standard. So feel free to go through these and utilize all of these different resources that are available here. Every single one at the bottom of the list of resources has a link to a spreadsheet. And this is another thing that I put together. This spreadsheet gives you various sensors as well as various suppliers of those sensors. And, each supplier kind of has their strengths and their weaknesses. I even have included some of those up here. Some of them have special types of connectors that make things easier. Most of them provide right on their websites sketches that you can use to upload to Arduino or libraries. The only place you're not really going to find those are on Amazon. I would generally say to maybe use Amazon as a last choice, just because there is not much in the way of technical support available, and it's easy to get um, non-genuine or like counterfeit parts on there that have mm, dubious um, they just might not work. Let's just put it that way. I've had situations where we've run into that here at Teachers in Space. One of our workshops, we saw that we could get a bunch of Arduinos for a fraction of the price by going through Amazon, but it turned out that 50% of them didn't even work. So we didn't wind up saving money anyway. So you might be tempted to save money by using Amazon, or I've seen a lot where school districts, it's easy to get stuff from Amazon through your school because your school already has it in their system and it's all set up. Um, but if you can, I would recommend either Adafruit or SparkFun or DF Robot. They provide the higher quality products, and you're much less likely to run into situations like we ran into where like half the stuff doesn't work. And they also have a lot of good technical support. If you do run into an issue, they can usually answer your questions in a timely manner. And I've had to do it. I have reached out to Adafruit, I've reached out to DF Robot, and I've had my questions answered within 24 hours. Then a couple more resources. Not all of these are current at the moment, but there are some grant programs available to get resources for your builds if that's necessary. So use all of this as best you can. And again, ultimately, if you're looking through all this and you're still feeling a little overwhelmed or your question isn't being answered, just reach out to me. This is what I do. I'm, a lot of the times I'm just waiting for you guys to send me an email or give me a phone call or whatever, so that we can get you and your students going. All right, so I'm going to stop here just for a second in case anybody has any preliminary questions. Also to admire Chris's cat, which is an amazing cat.
Dory,
Have one.
Dory's very happy to be a part of the meeting today.
Beautiful cat. I've got 3 cats around somewhere, but they're over by the wood stove, probably staying warm. So does anybody have any questions at this point? Sure, McKenna.
Yeah, and I'm sorry if this has been answered previously, but do you have some like the STL files for what you've 3D printed and sent us if we wanted to, like you said, create more or less a classroom example as well to keep?
Yes. Yep.
Okay.
So right now I'm in the process of completely remaking the Teachers in Space website, but currently if you go on to tis.org and you go to the resources drop down, one of the drop downs is called Build It. And if you open that Build It page, you'll see there is a zip file that has the STL files for the actual CubeSat frame.
Awesome. Thank you.
You're welcome. Any other questions at this point? All right, then I am going to. Oh, Shoshana, you have a question?
Yeah, real quick. Just my students are interested so far in making some comparisons with light, and the only sensor we have is the photo sensor. Would you recommend something else?
So the photo sensor that comes in the kit is a photo resistor, which that works perfectly fine. I think that most of the other types of sensors that look at light generally use photoresistors. There are some environmental sensors out there, especially from DF Robot, that also have UV light sensors. So that might be something that they might be interested in as well. A lot of the light sensors that you'll find, whether through Adafruit or DF Robot or SparkFun, will have both visible light and UV light all in one little package.
Okay, thank you.
You're welcome. And so, yeah, again, that spreadsheet that I showed you earlier, that has the environmental sensors on there. It has looks like, yeah, it has photoresistors as well. But one of those photo or environmental sensors, especially the one from DF Robot, I really like because it has, I think, 7 different data points that it collects all in one little sensor package, which makes it really convenient to be able to fit into a CubeSat. Any other questions before moving on? All right. Let me share my screen again. So I'm just going to take a look at a couple of the currently submitted proposals, just so that you can see, what they look like, what other people's look like, to kind of get an idea of what it is that people are submitting. All right, so this one says, the proposed CubeSat experiment to be conducted by 5th grade students aims to gather comprehensive magnetic field and motion data during a high altitude balloon mission. So they are going to be using a magnetometer, as well as the LS76DSOX, which is going to be a accelerometer / gyroscope. as well. Okay, so so what they have here is a 9 DOF, or degree of freedom, IMU, which stands for inertial measurement unit. So that is a single sensor package that would include a magnetometer, so that's 3 of your degrees of freedom, an accelerometer, which is another 3 degrees of freedom, and then a gyroscope, which is the last 3 degrees of freedom. So all 3 of those sensors all fit on one tiny little chip. So I would recommend including something like this in every single CubeSat experiment, just because um, having like the orientation and the movement of the CubeSat is going to make comparing other data points that much easier. As an example of that, I'm going to show you some of the data real quick from one of our Blue Origin CubeSats, because I had to actually wind up using that data in order to figure out some of the other data. All right, so let's zoom in here a little bit. So here on the accelerometer on this graph, you're actually able to see various points in the flight, various events in the flight, just based on the accelerometer data alone. And so, you could see that for a while, the CubeSat was just sitting there in the capsule, nothing was happening. And then probably something was engaged or disengaged, and you see a little blip right here. And then you can see where the engines were actually kick on. And you can also see where max Q happens, where they throttle down the engines for maximum aerodynamic pressure. And then you can see where they throttle them back up again once they get to that point. And then you can see also where main engine cuts off, and halfway between where the main engine cuts off and where you start seeing the descent or deceleration. So you have deceleration and then you have acceleration again. So this is where your apogee was. And you can see where the parachutes and the landing took place. Now, the reason why this is important is when you look at other events or other types of data, you can line things up. So, for example, there was a microphone on this CubeSat, and this actually helped figure out when those events were taking place. So you can see ignition, this very loud spike. This is when the engines were turning on. You can see where at max Q, where they start throttling the engines back down again. And then you can see a little bit of a acceleration here. Now, as they were reaching those higher altitudes, there's probably less noise that was actually being, heard, because there's just less atmosphere outside. And then you could see here on the landing a little, probably like a thump that took place. Plus, the capsule on Blue Origin's New Shepard has little rockets that go off like a second before, or even less than a second before it hits the ground. And that's probably what you're hearing right there. And then this is probably when they open the capsule up, and you could hear people probably, talking inside there, or just the sounds of opening the hatch and whatnot. So you wouldn't necessarily think that acceleration and the accelerometer and a microphone would be all that related to each other, but here we are. I was actually looking at the microphone data in order to really figure out what the events were in the acceleration data. So can be helpful to have like a baseline of certain sensors on your CubeSat. We worked with them in the online course and in the in-person workshops. So I would, at a minimum, include, um, the accelerometer, gyroscope, definitely the micro SD card reader, because otherwise you're not going to be able to save your data anywhere. And then some form of environmental sensor, whether it's a visual light sensor like a photoresistor, temperature, pressure. Again, I'm going to go back to that environmental sensor I've mentioned a couple times now from DF Robot. That's like a really great one. Adafruit also has a few of them that will combine various environmental data sensors into a single little package. That means that you can it'll be easy to fit. Really, the sensors are probably not going to be your limiting factor unless you're working with really big ones like a radiation sensor. It's everything else that's probably going to get you first. Whatever you're using to wire everything together, like a breadboard. Those are actually kind of big and bulky and even kind of heavy. So you may decide to go with an even smaller breadboard than the half-size mini breadboards that we use in our kits. They have even smaller ones. If you don't need all of those spots, you could get away with using a smaller breadboard, and that might save you at least some weight and some volume. So yeah, as you can see here, this is just 3 paragraphs. Explains, the sensors and what the students are getting at. So this is perfect. They even included some links to the actual sensors that they're going to use. So this is great. You know, this is what we like to see. Let's take a look here. So an atmospheric layering study. So measuring air temperature and pressure during ascent to study atmospheric layers. Specifically, measure temperature and pressure profiles throughout the troposphere and stratosphere. Compare temperature elapse rates in different altitude ranges. Identify the tropopause and stratopause boundaries. And analyze how temperature and pressure vary across different latitudes, if possible. So they're thinking that they're going to fly this CubeSat multiple times. So they'll start with this flight in this program, and then they'll probably fly with other organizations as well. So this, I know, is one of the teachers from Maine and Maine Space Grant Consortium, as well as the University of Southern Maine, have a great ballooning program, and they fly student experiments all the time. And I'm pretty sure that you can find an organization in every single state that does these types of high altitude balloon missions. There's hundreds, if not thousands, of balloon flights every single day just for weather alone. Um, you know, a lot of our weather forecasting relies on these types of flights. So universities all over the place are constantly doing these. Other types of organizations, weather organizations, are constantly doing these. I highly recommend looking in your state and reaching out to folks, because a lot of the times these balloon missions, they have a lot more capability. They can fly extra payloads on them if necessary. And to be able to fly a student made CubeSat from that state, I'm sure any university would be very happy to do that. So don't think that this is the end of your CubeSat flights. Once we do the flight in March or April, we're sending you your CubeSat back to continue using as a learning tool. So use it as much as you can, whether it's in or around your classroom or on other flights. Not to mention, we will be taking the designs of all of the experiments, and we're going to be integrating them into a 2U CubeSat or multiple 2U CubeSats that will fly on Blue Origin again, and potentially other flight providers in the future. So while it won't be the actual hardware that you and your students work with, it will be based on the hardware that you and your students work with. All right, let's look at another one. So in this one, they're going to be investigating the effect of plasma on bush green beans. So this is a cool one because it involves some biology. We haven't flown too many biological payloads yet, so I'm happy to see this kind of thing taking place. So in space, plasma is one of the most common states of matter. According to the article, The Seed of an Idea, the fourth state of matter, plasma, could make seeds germinate faster and potentially increase the yield of the crop. So not only is this interesting because it's biology based, but also it has a very real usage. You know, increasing crop yields is something that is very important to a lot of people down here on Earth. And this is one of those great examples of why are we even bothering, with space? We have all these problems here on Earth. People will say, why are we wasting time, money, and resources on going to space when we need to fix, our planet first? Well, this is a good example of how going to space allows us to make those improvements down here on the ground. So I'm really hopeful that, more of you will work on some of these biological based payloads as well. I think that that's really cool. So to conduct this experiment, looks like they're going to be sending some seeds up on the flight, and then they'll have some controls that they'll keep down on the ground, and then they will plant all the seeds and see what happens based on, whether the plants went to the edge of the atmosphere or not. And this is a perfect segue into future, orbital or suborbital flights on rockets, because they'll be able to really send those seeds up into space and see how they are affected. We actually flew um, on a zero-G flight where we had a teacher who was interested in this similar idea, and she brought some seeds with her and actually um, had the seeds in little compartments that she added. I believe it was like a nutrient solution to while in zero G to see if that had any effect on the seeds.
Hey, Noah, this is Jim. I saw Melissa raise her hand while you were going through that. I wonder if you have time to
Yeah, sure.
ask.
Melissa, this is Melissa's proposal. So do you have something you want to add?
Yeah, I'm sorry, but I didn't send you the latest one. They actually listed the sensors too. I'll
Oh,
forward
nice.
to you later what kind of data they were going to collect with the sensors while it was up there and compare it. They just got me the update yesterday, so I didn't forward it to you yet. So
All
I
right,
will.
that's fine. Yeah, as soon as whenever that's available, go ahead and send it over. Look forward to seeing it. All right, let's take a look at another. All right, so this class is building a CubeSat to conduct an experiment focused on measuring both speed and temperature in space. Interesting. So they want to test the CubeSat speed by measuring the distance it travels and the time it takes to cover that distance. Compare the CubeSat speed as it moves upward and downward to better understand how gravity affects its motion. Yeah, this is great. Your students will learn something. I guarantee it, no matter how simple or advanced, how complex or not complex that your CubeSat is. Just the process of building it and going through that engineering design process, your students will learn a lot. I always tell these stories because I think that they are kind of the the crux of this entire program, which is that your students need to learn about perseverance more than probably anything if they want to go work in the space industry one day. We've had, if you watch interviews with CEOs of rocket companies or people who work at rocket companies, a recurring theme is the idea that they can learn or be taught the things they need to do to get their job done when they start working for a company like SpaceX or Blue Origin or Firefly Aerospace or Blue Shift Aerospace. But you can't necessarily just like learn perseverance on the job. You can't learn troubleshooting on the job necessarily. That's one of those things that the students will want to have before they start applying for those jobs. So getting started with this project at as early an age as possible they are definitely going to have to do some troubleshooting. Like, as you have all experienced now, whether you've been to an in-person workshop or you've done the online course, you know, it doesn't go right, the very first time. I've never experienced anybody, getting everything right on their very first shot. Something always goes wrong, whether it's a wiring mistake or there's something going on with their computer or something is just not working and trying to figure out what part is causing the problem, whether that means unplugging things one by one and verifying that they work. This entire process is going to be immensely beneficial to you and your students. So, you know, we've looking back at the um, that update that I had showed you earlier with all of the other CubeSats that were built by other classrooms. Some of them are extremely complex, and which means more troubleshooting, and some of them are super simple. Um, if you're teaching kindergartners or second graders, you don't need to have anything too crazy. um, you might just have like a temperature sensor on there or a accelerometer on there, and that alone will be able to get lots of different data that your students will be able to look at in the end. But really, the most important thing is them actually putting it together.
No, Sarah raised her hand during that discussion there.
What do you have to add, Sarah?
Sorry, it was an accident.
Oh, you're just so excited because we're reading through your proposal.
Yes, that's what it was.
Yeah, so no, this is great. So in addition to speed, the CubeSat will measure temperature changes in space. We are interested in how temperature in space compares with temperature on Earth, particularly during different seasons. That's another great thing about these CubeSats. They work as really good little weather stations. Pretty much, every single CubeSat is its own little weather station because they almost always have some sort of temperature or pressure sensor in them. So, you can, and climate science is very important these days. I was just mentioning earlier about all of the fires that are happening around the country. It seems like there's lots of uh, storms in the Gulf of Mexico and Caribbean this time of year, um, kind of in a record-setting way. I think is it Hurricane Sarah that's brewing right now? Um, but we just had another one just before like earlier this week. This is all data that will be relevant to us more and more as time goes on. um, whether you want to believe it or not, it seems as though climate science is becoming a more and more important part of all of our lives. So just because this is teachers in space doesn't necessarily mean that you're only going to be using these CubeSats for space research. You can also use these in your classroom, in your communities, outside the classroom. We had a Maine teacher and her students who, built great CubeSats that we flew on zero G on the Perlin Stratospheric Glider. The design went into Blue Origin CubeSat. They took everything that they learned during this process and they're now building all sorts of environmental monitoring setups where they're monitoring water quality and air quality, which is very important to folks in Maine. They are very dependent on their fishing and um, their tourism up there, and so their students want to learn more about what's going on with those resources. So while these are CubeSats, they can be used for all manner of different, scientific endeavors. So don't feel as though you're limited to just space science. So what we've seen now in a few of these proposals is that some of them are geared specifically towards space, which is awesome. Some of them are geared specifically towards flying on a high altitude balloon and collecting atmospheric data. That is also awesome. So don't think that you have to, um, you know, pigeonhole yourself into one specific type of flight profile, because there are lots of different flight profiles depending on the flight platform. So whether it's a suborbital flight, whether it's on a rocket or a balloon, or if it's, you are thinking about the orbital flights. While we won't be able to fly your specific hardware on an orbital flight, we could one day, take that design and build it into an orbital CubeSat. That's what we've done multiple times now with our Serenity CubeSat. We had a experiment that's been on all three of the Serenity builds that we've flown, that was designed by a sophomore in high school. That was 8 or 9 years ago now when he first came up with that experiment, and now he's finishing up his doctorate in aerospace engineering. So, don't limit yourself or your students. If they want to design an experiment specifically for space flight, encourage them to do that. It won't necessarily fly into space during this cycle of this program, but that doesn't mean that it won't eventually. And that also doesn't mean that they can't eventually fly into space themselves. You might have a middle schooler right now who comes up with this idea, and you guys build this CubeSat, and who knows, in 8 or 10 years, they might be working for NASA or SpaceX or Blue Origin, and this could be a stepping stone for them to get there. So I'm going to stop there and utilize the remainder of our time to answer any more questions that folks might have at this point. I'll also take a look at the chat and see if there's questions in there. A whole lot of note takers. This is like a new phenomenon. I haven't ever seen this before. Just like the last 2 months, these AI note takers have really been a big thing. So does anybody have any questions? I see Robin, was that a bunch of students that we got there? Cool. You guys are going to build an awesome CubeSat for us, right? Yeah. I see some hand waving. I want to see some head nodding. That's what I want to see. Yeah. All right, cool. All right, so I mean, if there aren't any questions for right now, I know that, as soon as you log off, like the question might come to you, as often happens. Again, my virtual door is always open. So definitely, if you come up with a question at a later point in time, feel free to get in touch with me. I will help you in any way that I can, whether that's, sitting down and brainstorming with you, coming up with ideas, or if you want me to speak with your students directly to answer their questions. I know it can be overwhelming sometimes when you've got like multiple classes and all these different students have questions, and maybe you don't feel, confident that you have the answers. Just pass them along to me, and I will do the hard work for you.